Hello everyone. In this video, we'll be going over the AP Physics C Mechanics 2012 practice exam created by the College Board. As a disclaimer, I do not own any of the questions listed below. They are the property of College Board, which does not endorse this product. Below are my own solutions to this exam. Here is the formula sheet developed for the 2012 exam. You can come back to this part of the video at any point in case you need the equations on the left. Let's begin. To start, let's assume that a ball is struck at time t equals 0 and follows the given parabolic path. The following show graphs which have quantities possibly associated with the motion as a function of time. Assuming that air resistance is negligible and that the positive direction is upwards and to the right, we wish to answer the following two questions. Firstly, which graph represents the horizontal component of the velocity of the ball? Well, looking at the parabolic path of the ball, at each moment in time, we have some velocity to the right and some velocity in the vertical direction. As we move up this parabolic path, the horizontal velocity is constant because nothing is slowing it down as we're neglecting air resistance. At the top of the path, there is only motion in the horizontal direction, so that the ball freezes in its vertical motion at the top. Then, as it comes back down, it begins to gain vertical velocity in the downwards direction. Then, all the way at the end of the path, it has its greatest velocity, which is now in the negative direction. So, we know that the graph for the horizontal component should be constant. So, the answer to 1 is E. Then we wish to find the graph which represents the vertical component of the velocity of the ball. Well, as we see here, we know that initially it's positive and the largest it can be. At the midpoint, it is 0, and at the end, the vertical velocity is the most negative that it can be. The only graph here that follows all of those criteria is D. So, the answer to 2 is D. Next, let's assume that an object with an initial velocity of v0, as shown in the diagram above, slides up and then down a long and frictionless inclined plane. Which of the following is true of the object as it moves? Well, we know that there is no friction force acting on the object. So the free body diagram of this object, at any point along the ramp, whether it's moving up or down, is that it has a single force, which is the gravitational force. Since this gravitational force is simply equal to m, the mass of the object, times g, the gravitational acceleration due to gravity on Earth, we have that the acceleration should be constant along the entire path up and down the ramp. So the answer is D, as the acceleration is the same as it moves up and down. Next, let's assume that we have two blocks of masses m1 and m2, and they are connected by a massless string, which then passes over a wheel of mass m, as shown above. The string doesn't slip on the wheel and exerts forces T1 and T2 on the blocks. When the wheel is released from rest, in the position shown here, it undergoes an angular acceleration and rotates clockwise. Which of the following statements about T1 and T2 is correct? Well, we know that there has to be some net torque in the clockwise direction. And further, the tension acts on the wheel both here and here, where this is T2 and the one on the left is T1. Then we see that T2 must be greater than T1 so that there is a net torque moving down in this diagram, meaning that the string block system will rotate clockwise. So the answer here should be E. Next, suppose that we have three objects which are located along the x-axis as shown in the diagram above. We then wish to find the center of mass of the objects. Well, the formula for the center of mass is given by the center of mass position is equal to the sum indexed by I over all of the masses multiplied by their positions divided by the sum over all of the masses. So here we have that, well, we have a 3 kilogram mass at the 0 position. So we have 3 kilograms times 0, as 0 is the position. Then we add this to a 5 kilogram mass at the 3 position. So 5 kilograms times 3 meters plus the 2 kilogram object at the 5 position. So plus 2 kilograms times 5 meters. And we divide this by the sum over all of the masses. So 3 plus 5 plus 2. 3 plus 5 plus 2. Then the numerator becomes 15 plus 10, which is 25, divided by 10. So the answer is 25 divided by 10, or 2.5 meters, is the center of mass location. So the answer here is D. Next, which of the following is equivalent to a unit of momentum? Well, we know that the change in momentum, delta P, also known as the impulse, is equal to the integral of F times dt, or for a constant force, it's equal to F times delta T. So we have that the units of momentum on the left, which is indicated by square brackets with P in between them, this should be equal to the units of force, F in square brackets, times the units of time in square brackets here. And that's simply because we have P is equal to F times delta T, so the units of P should be the units of F times the units of T. Well, the units of F are newtons, and the units of time are seconds, so the units of momentum are Newton seconds. So the answer here is D. Next, suppose there are two objects which are dropped from rest from the same height. Object A falls through a distance dA during a time t, and object B falls through a distance dB during a time 2t. If air resistance is negligible, what is the relationship between dA and dB? Well, recall that the kinematic equation for distance is d is equal to v naught t, where v naught is the initial velocity, plus 1/2 a t squared. Here, we start both masses from rest, so that this should be equal to g over 2 times t squared, where I've used g because that is the acceleration in this problem. Then, we have two cases, one where we're dealing with the A object, and one where we're dealing with the B object. For the A object, we travel a distance dA in time t. That is, we have the distance dA is equal to g over 2 t squared. For object B, however, we have that it travels a distance dB in time 2t. So we can write dB is equal to g over 2 times 2t all squared, which is equal to 2g t squared, because the 2 is squared, so we get 4, which divided by 2 is 2. Then, solving both of these equations for t squared, we find that on the left, t squared is equal to 2 times dA over g. And for b, we find that t squared is equal to dB over 2g. Well, t squared is the same for both of these objects. They both have the same time t. Then we can equate these two t squares so that we write 2 times dA over g is equal to dB over 2g. Canceling out the g's and solving for dA, we find that dA is equal to dB over 4. So the answer to this question is A. Next, let's assume that the maximum mass that can be hung vertically from a string without breaking the string is 10 kilograms. A length of this string that is 2 meters long is used to rotate a 0.5 kilogram object in a circle on a frictionless table with the string horizontal. The maximum speed that the mass can attain under these conditions without the string breaking is most nearly which of the following? Well, to start, we know that the maximum tension that this string can withstand is given by the gravitational force of a 10 kilogram mass. That is, the max tension, which I will call T max, is equal to the gravitational force of a 10 kilogram mass. So it's equal to 10 kilograms times the gravitational acceleration, which is g. On the AP exam, you assume that g is 10, so the max tension is 100 newtons. Then we rotate this string on a horizontal table. Horizontal here simply means that we can forget about gravity, and we wish to find the maximum velocity or the maximum speed that this string mass system, which is rotating, can attain. Well, the force in question here, whenever you're dealing with rotating objects, is going to be the centripetal acceleration, Fc, which here is equal to mv squared over r. Then, plugging in for what we know, we have a 0.5 kilogram object. So 0.5 kilograms is the mass times the velocity squared divided by, well, we have a string of 2 meters in length. So the radius here is 2 meters. And we wish that this be equal to 100 newtons, as that's the maximum tension that the string can withstand. Solving for V, we find that V squared is equal to 400, or that V, the maximum speed, is equal to the square root of 400, which is 20 meters per second. So the answer here is D. Next, suppose we have an object moving on a horizontal frictionless surface, which then makes a glancing collision with another object initially at rest on that surface. In this case, which of the following is true about momentum and kinetic energy? Well, when it comes to these collisions, we know that momentum is always conserved. So that eliminates any of these answers where it says that momentum is not conserved. So we know the answer is not E, and that the answer is also not B. Then the kinetic energy is only conserved if we have an elastic collision. So, since that information is not given to us, we know that the answer must be A, as the momentum is always conserved and the kinetic energy may be conserved depending on if the collision is elastic or inelastic. Next, suppose we have a particle of mass m which starts from rest at position x0 and time t0. It then moves along the positive x-axis under the influence of a single force given by Fx, which is equal to b times t, where b is a constant. The velocity of the particle is given by which of the following? Well, we know that the force Fx is equal to bt, and that all forces are equal to ma. And further, we know that A is equal to dv dt, where v is the velocity. Then, solving for v, or solving for A first, we know that A of t is equal to b times t over m. Then, we know that A of t is really the time derivative of the velocity. So, integrating both sides of this equation, we find that we have v of t minus v of 0 is equal to the time integral of bt over m dt. Well, we're given that the mass starts from rest, so we know that v of 0 is 0. Then, integrating on the right, we find that v of t is equal to b over m times t squared over 2 evaluated at 0 and t. Then, this is b over m times t squared over 2 minus 0. So the answer here is that the velocity is equal to bt squared over 2m. That is, the answer is B. I suppose as a quick technical note, I can point out that for the integral here on the right, we should say that we have t prime and dt prime here, because we're already using t as a bound on the integral. So, so that there's no confusion, the actual integrand should be t prime. Regardless, the answer is still B. Next, let's assume that we have 3 blocks, A, B, and C, of masses 1, 2, and 3 kilograms respectively, which are initially at rest on a frictionless surface, as in the figure above. What force F has to be applied on block C to accelerate the 3 blocks at 2 meters per second squared? Well, the total mass of all 3 blocks connected to each other is 6 kilograms. Then we wish to find a force F, which is always equal to ma, which accelerates these blocks at 2 meters per second squared. So we already know the total mass, that's 6 kilograms, and we know the desired acceleration, which is 2 meters per second squared. So the force is simply 6 times 2, which is 12 newtons. So the answer here is E. Next, let's assume there's an electric motor which provides a 0.5 watts of mechanical power. How much time will it take the motor to lift a 0.1 kilogram mass at constant speed from the floor to a shelf 2.0 meters above the floor? To start, we know that power for a constant amount of work is equal to delta W over delta T, where delta W is the work, the difference in the work being done, and delta T is the time. Then we further know that for a constant force, the work is equal to F times delta R. And since we're moving the mass with a constant speed, as indicated in the problem, that means there's a net zero acceleration. So constant speed implies that the net acceleration is 0, meaning also that the net force is equal to 0. This implies that the force due to gravity should exactly equal the force given by the electrical motor. That is, the force due to gravity is exactly equal to the force from the motor. And because the force due to gravity is equal to mg, which here, since we're raising a 0.1 kilogram mass, is equal to 0.1 kilograms times 10 meters per second squared, the force due to gravity is 1 Newton. So this also means that the force from the motor is 1 Newton. Therefore, the work from the motor, Wm, which is equal to the force from the motor times the displacement of the mass, is equal to 1 Newton times the displacement. We're displacing by 2 meters, so that the total work being done is 2 joules. Finally, we find that the total power, P, which is equal to 0.5 watts, is equal to 2 joules divided by delta T, which is what we wish to solve for. Then, solving for delta T, we find that delta T, the time elapsed, is equal to 4 seconds. So the answer here is E. Next, let's assume that a block slides from rest with negligible friction down the track above, descending a vertical height of 5 meters to a point P here at the bottom. It then slides over a horizontal surface. The coefficient of friction between the block and the horizontal surface is 0.2. We wish to find how far the block slides on the horizontal surface before coming to rest. Well, to start, we know that the energy at the top of the ramp, U0, is equal to gravitational energy, which here is mgh. Then, although we're not given the mass of the block, we'll assume that it has some mass m. Knowing the height and the gravitational acceleration, we find that the potential energy of gravity is equal to the mass m times the gravitational acceleration 10 times the height 5. So this is 50 times the mass. Then at the bottom of the track, at point P, all of this gravitational potential energy is converted into kinetic energy. So the kinetic energy at P is equal to 50 times m, where m is again the mass of the block. Then, as we know along this horizontal surface, the frictional force is constant. We find that the work being done by the rough surface is equal to F, the frictional force, times delta R, which is what we wish to find. We wish to find this quantity. And since work has units of energy, we have to exert 50 times m units of energy. So 50 times m joules has to be exerted by work from the frictional force in order to stop this block completely. Here, F is equal to the frictional force, which we know is the coefficient of friction times the normal force. So, as the normal force is just mg, the force due to gravity, we have that the frictional force is equal to mu, the coefficient of friction, times mg. And as we're given mu, and we know what g is, we find that the frictional force is equal to 0.2, which is the coefficient of friction, times m, the unknown mass, times 10, the acceleration due to gravity. So this is equal to 2 times m. Then we have the above equation, which says that 2 times m times the displacement delta r is equal to 50 times m. We notice now that the m's cancel, so the mass of the block doesn't matter. Then, solving for delta r, we find that the distance that the block can travel before it comes to rest is 25 meters. So the answer here is E. Next, let's look at the graph above, which shows the velocity is a function of time for an object moving along a straight line. For which of the following sections of the graph is the acceleration constant and non-zero? Well, a constant acceleration implies a linear velocity with a non-zero slope. that is, a constant acceleration, implies a linear velocity with a non-zero slope. So, here there are only two sections that have a linear velocity with a non-zero slope. These sections are RS and ST. So the answer here is D. Then let's assume that the velocity of a particle moving along the x-axis is given as a function of time by the expression v of t is equal to 3t squared minus 2t plus 4, where v is in meter per second and t is in seconds. We wish to find the acceleration of the particle at time t is equal to 2 seconds. Well, we know how to find the acceleration from the velocity. That is, a of t is equal to the time derivative of the velocity, which here is given by 6t minus 2. We just take the time derivative of this function here. Then we wish to find the acceleration at t is equal to 2. Plugging in for t is equal to 2, we find that the acceleration is 6 times 2 minus 2, which is equal to 10. So the answer is D. Next, let's assume that an unstretched ideal spring hangs vertically from a fixed support. A 0.4 kilogram object is then attached to the lower end of the spring. The object is pulled down a distance of 0.35 meters below the unstretched position and released from rest at time t is equal to 0. A graph of the subsequent vertical position y at the lower end of the spring as a function of time is given in the plot above, where y is equal to 0 when the spring was initially unstretched. At which of the following times is the upward velocity of the object the greatest? Well, let's look at the plot above. We know that this orange line that I'm drawing is the position about which the mass is oscillating. So that is the stretched equilibrium position when the mass is hanging. So the maximum upward velocity should occur when it's passing through this equilibrium position, because at the top and the bottom here, we see that the tangent line to this plot is 0. So we wish to find when the tangent to this plot as a function of time, or dy dt, which is the vertical velocity vy, is the greatest. This occurs at this position here. So the answer here should be B, 0.25 seconds. And we know that because when we project onto the t-axis, it's halfway between 0 and 0.5, which is 0.25 seconds. Then we wish to find the spring constant of this spring. To do this, we look at the free body diagram of this mass. The downward force here is gravity, and the upward force is the spring force given to us by Hooke's law. In equilibrium, we know that these forces should be equal to each other. So, since the spring force is equal to negative kx, Here, let's suppose that we're in equilibrium, which is this orange line that I indicated. That is the stretched equilibrium position. Then, the x position is negative 0.25. So, the spring force is equal to negative k times negative 0.25, which here, the negatives cancel, and since 0.25 is 1/4, we find that the spring force is k over 4. Then, the gravitational force is equal to mg, which here, since we have a 0.4 kilogram object, is equal to 0.4, the mass, times the acceleration due to gravity, which is 10 meters per second squared. So this should be equal to 4. But in equilibrium, these two forces are equivalent. So in equilibrium, we should find that k over 4 is equal to 4. Solving for k, we find that k is equal to 16. So the answer here is A. Next, let's assume that identical net forces act for the same length of time on two different spherical masses. Which of the following describes the change in linear momentum of the small mass compared to that of the larger mass? Well, to answer this, we first note that we have two forces, F1 and F2, which are equivalent to each other. Then, we know that these forces should be equal to the change in momentum divided by the change in time. Then, F2 is also equal to the change in the second mass's momentum divided by the change in the time. Equating these two, we find that delta P1 divided by delta T is equal to delta P2 divided by delta T. These delta T's are the same, so we can cancel them. What we find then is that the change in the first mass's momentum should be exactly equal to the change in the second mass's momentum. So the answer here is C, as we found that the change in the linear momenta of the two masses, independent of the actual values of their masses, is equivalent. Next, let's assume that we have a uniform thin rod as shown above with mass m and length L. The moment of inertia of the rod about an axis through its center, given here, and perpendicular to the rod is 1/12 times the mass times the length squared. We wish to find the moment of inertia of the rod about an axis perpendicular to the rod passing through point P, which is halfway between the center of the rod, which I drew in orange, and the end of the rod. To do this, we first note that the rod has uniform density. That is what uniform here means. It has uniform density. So, the density of this rod, which is the mass divided by the length, so m over L, since it's uniform, it should be equal to dm dr, where here dm is an infinitesimal mass of the rod, and dr is an infinitesimal length along the rod. So it's given by this very thin sliver here that I've just drawn. Then, solving for dm, we find that dm is equal to m over L dr. Then, we note that the moment of inertia for any object, I, is equal to the integral of r squared dm. Plugging in for what we have, noting that since we're integrating about the position p, we assume that p is the new r is equal to 0. So this end of the rod has a position of r is equal to L over 4. And the left-hand side of the rod has a position of r, which is equal to negative 3L over 4. And that's when we assume that p is the 0, the r is equal to 0. Then, plugging in for dm, which we just solved for above, this integral becomes the integral from negative 3L over 4 all the way up to L over 4. We're integrating m divided by L, r squared dr. Then, doing this integration, we can pull out the m and l as their constants. So this is equal to m over L times 1 over 3 r cubed, evaluated at negative 3L over 4 and L over 4. And pulling out the 3 as that's a constant, we get m over 3L times L cubed over 4 cubed minus 3 cubed L cubed over 4 cubed. And there should also be a minus inside of here, because negative 1, which is what this minus is, to the third power is still negative 1. Then, simplifying this, we can pull out an L cubed, and the negatives cancel to become a positive. So we have m L squared, because the L in the denominator cancels with one of the L's that we've pulled out, divided by 3 times, well, 4 cubed is 64, plus 3 cubed, which is 27, over 64. Adding these together, we get m L squared over 3 times 28 over 64. 28 over 64 can be simplified to 7 over 16. So we get m L squared times 16 divided by 3 times, this is 7 over 16. Then 3 times 16 is 48, so that the final answer is 7 over 48 mL squared. So the answer here is E. Next, let's assume that a certain one-dimensional conservative force is given as a function of x by the expression F is equal to negative k x cubed, where F is in newtons and x is in meters. We wish to find a possible potential energy function U for this force. Well, conservative forces have a special form. Conservative forces a conservative F can be written always as negative du dx, where U is some potential energy function. So here, all we wish to do is find a U whose derivative with respect to x times negative 1 is equal to the F that we wish to find. Just going down the list, we find that when we take the derivative of d with respect to x, so here du dx is equal to k x cubed. And multiplying by negative 1, So we have a minus on either side. This is exactly the force that we wish to find. So the answer is D. Next, which of the following is a different equation that correctly describes Newton's second law for a simple harmonic oscillator of mass m and a restoring force constant k? Well, Newton's second law states that the net force is equal to ma, and a simple harmonic oscillator obeys the spring equation, which is negative kx. Then a is the second derivative of x with respect to time. So this can be rewritten as m d squared x over dt squared, which is equal to negative kx. So this is a differential equation for x. And this matches with b. So the answer is B. Next, the elliptical orbit of a comet is shown above. Positions 1 and 2 are, respectively, the farthest and nearest positions to the Sun, and at position 1, the distance from the comet to the Sun is 10 times that at position 2. At position 2, what is the comet's kinetic energy? Well, we know that the velocity of orbits such as this, elliptical orbits, have their smallest value when they are farthest away, and when they are nearest, so at position 2, they have their largest value, where these are velocities. And we know that from Kepler's laws. Then, the kinetic energy, which is equal to 1/2 mv squared. Well, since we have a v here, the kinetic energy should have its maximum value when the velocity is maximized, and that occurs at position 2. So the kinetic energy should be at its maximum value. So the answer is C. We next wish to find what is the ratio v1 over v2 of the speed of the comet at position 1 to the speed at position 2. Well, here we know that the gravitational force is exactly equal to the centripetal force, because this is the only force acting on the comet. And since it's moving in a circular orbit, a roughly circular orbit, we assume that it's roughly circular. We can find the centripetal force. Here, the gravitational force is g, Newton's constant, times the mass of the comet, times the mass of the Sun, divided by the radius, r1, squared. And this is for position 1. And this should be equal to the mass of the comet times v1 squared divided by r1. So what we find is that v1 goes as 1 over r1. And similarly, what we can find is that v2 goes as 1 over r2. So v1 over v2 should go as r2 over over r1. So here, let's assume that r1 is equal to that r2 is equal to some r value. We won't specify what it is. From the statement of the problem, we know that r1 is equal to 10 times r2. So it's equal to 10r. So V1 over V2 should be 1 over 10. Next, we wish to find the ratio F1 over F2 of the force on the comet at position 1 to the force on the comet at position 2. As we did above, the gravitational force Fg is equal to Newton's constant g times the mass of the comet times the mass of the sun divided by, let's say, r1 squared. That's for position 1. And similarly, Fg2 is equal to gmm over r2 squared. So this implies that Fg1 over Fg2 is equal to r2 squared over r1 squared. And using these values for r1 and r2, we find that this is equal to r squared over 100 r squared, which is equal to 1 over 100. So the answer here is A. Next, a block of mass m is pulled across a rough surface as shown above. The coefficient of friction between the block and the surface is mu k. The force F that pulls the block is exerted at the angle phi shown. Which of the following is an expression for the magnitude of the frictional force on the block if it is moving at constant speed? Well, let's look at the forces acting on this block, where for convention, we know that g is equal to 10, and that g, the gravitational acceleration, points down. Since 10 is positive, we'll assume that the down direction is positive. So this is the positive x direction, moving down. Or we'll call it the y direction, let's say. Then, at this point on the block, we have down is the gravitational force. And this vector F can be decomposed into a horizontal force and a vertical force. This vertical force F, y, is equal to F times the sine of phi, just using simple trigonometry. Then the friction force, F friction, is equal to mu k, the coefficient of friction, times the normal force. The normal force is the net force acting in the vertical direction. Here, it's a sum of two forces, and assuming that the down direction is positive, we have that the frictional force is equal to mu k times, well, first we write the positive force, which here points down and is the gravitational force, and that's equal to mg. And then we subtract the force that points up, which is Fy. So we have minus F sine phi. So the answer here is E. Next, suppose we have two 4-kilogram blocks hanging from a rope that passes over two frictionless pulleys as shown in the figure above. What is the tension in the horizontal portion of the rope if the blocks are not moving and the rope and the two pulleys have negligible mass? Well, we know that the gravitational force here should be equal to the tension force, because we have a free body diagram on the block where we have the tension force pointing up and the gravitational force pointing down. And if this block is not to move, these two should be equal to each other. Then we have that T is equal to mg. Since we know m, and we always know that g is equal to 10, we find that the tension is equal to 4 times 10, which is 40. newtons. So the tension in the horizontal portion should be 40 newtons. Next, a person throws a ball of mass 0.2 kilograms. The ball starts from rest, accelerates horizontally, and uniformly through a distance of 0.9 meters, and leaves the person's hands at 30 meters per second. The average horizontal force applied to the ball by the person's hand is what? Well, since we're trying to find the average force, we know that the work done is equal to the average force times the displacement over which this force acts. Then, since all of this work is converted into kinetic energy, we know that the total work is equal to the kinetic energy, which is equal to 1/2 mv squared. Then we know m and we know the velocity, so this is equal to 1/2 times 0.2 times 30 squared. And we want this from the equation above to be equal to the average force exerted times the distance over which it is exerted, which is 0.9 meters. Then, solving for F, we find that F is equal to 1/2 times 0.2 times 30 squared over 0.9. This can be rewritten as 30 squared over 9. And 30 squared over 9 is equal to 3 squared times 10 squared over 9. Well, 3 squared is 9, so these things cancel. And we're left with 10 squared, which is equal to 100 newtons. So the answer here is D. Next, let's assume that a railroad car of mass 1,500 kilograms rolls to the right at 4 meters per second and collides with another railroad car of mass 3,000 kilograms that is rolling to the left at 3 meters per second. The cars stick together. We wish to find the speed of the two cars sticking together immediately after the collision. Well, we know here, as in all collisions, that the momentum is conserved. So the initial momentum, P naught, is equal to the final momentum, Pf. Here, the initial momentum, P naught, is equal to the momentum of the first railroad car, which is 1,500 kilograms times 4 meters per second, m times v, plus the momentum of the second railroad car, which is 3,000 kilograms times -3, where we have -3 meters per second because it's rolling to the left. So we have two cars, one going to the right and another car moving to the left. Assuming that the right is the positive direction, the car moving to the left has a negative velocity, hence the -3. Then, writing this out, we get 6,000 minus 9,000. And this should be equal to -3,000. And it should further be equal to the final momentum, which is equal to mv. But we already know the total mass. The total mass is 1,500 kilograms plus 3,000 kilograms as the carts stick together. So 1,500 plus 3,000 is 4,500. So we have 4,500 kilograms times the final velocity, or the speed, is equal to -3,000. So, since we don't care about the sign of the velocity, since we're just worried about the speed, which is the absolute value of the velocity, is equal to the absolute value of -3,000 over 4,500. And this is equal to 2 over 3. So the speed immediately after the collision is a, 2 over 3 meters per second. Next, let's assume that a meter stick of negligible mass is placed on a fulcrum so that the 0.4 meter mark is on the fulcrum. And at the 0 mark, we have a 1 kilogram mass and a 0.5 kilogram mass is being hung at the 1 meter mark. The meter stick is held horizontal and then released. Immediately after release, we wish to find the magnitude of the net torque on the meter stick about the fulcrum. So, using this drawing here, this point on the fulcrum is 0.4 meters. Then, the net torque, tau, is equal to the sum over the position of each mass times the force being acted by that mass. Here, we have one mass, which is 0.4 meters away from the fulcrum. So that's the 1 kilogram mass. So this is equal to 0.4 meters times the gravitational force of 1 kilogram, which is equal to 1 kilogram times g, which is 10. And then we subtract the torque from the other mass. Here, this mass is 0.6 meters away from the fulcrum, because this is a meter-long stick, and the fulcrum is at 0.4 meters. So to get to the 0.5 kilogram mass, you have to travel 0.6 meters. And we multiply by the 0.5 kilogram mass times the gravitational acceleration, which is 10. Solving this equation, we find that the net torque is equal to 1. So it's 1 Newton meter, or A. Next, an object undergoes simple harmonic motion along the x-axis shown above, where x is equal to 0 is the object's equilibrium position. Which of the following graphs best shows the relationship between the object's acceleration a and its displacement x from equilibrium? Let's assume that the positive a to be acceleration directed to the right. So, we know that the force F is equal to ma, and because this is simple harmonic motion, we know that this is equal to negative kx, or the spring equation, because that is our simple harmonic force. So, solving for a, we find that a is equal to negative k over m times x. But k over m is positive, as both k and m are positive. So the negative value means that we have a is equal to x times some negative constant. This is the equation for a line passing through the origin with a negative slope. So the answer here is A, as that's the only line with a negative slope passing through the origin. Next, assume that ball 1 is dropped from rest at time t is equal to 0 from a tower of height h, as shown above. At the same instant, ball B is launched upward from the ground with initial speed v0. If air resistance is negligible, at what time t will the two balls pass each other? Well, we know that from the kinematic equations, delta d1, the displacement, of the first ball should be equal to its initial height minus 1/2 gt squared, as g is the acceleration. And we have minus because we assume that that is in the down direction. Then delta d2 is equal to the initial velocity, v0, times the time elapsed, minus 1/2 gt squared. Notice that both balls are under the same acceleration due to gravity. We wish to find the point at which delta d1 is equal to delta t2. So we want to write delta d1 is equal to delta d2. Or, writing this out, we have h minus 1/2 gt squared is equal to v0 t minus 1/2 gt squared. Well, the 1/2 gt squared cancels on both sides. And solving for t, we find that t is equal to h over v0. So the answer is C. Next, suppose that the potential energy of a particle constrained to move along the x-axis can be described by the function u of x is equal to 1/2 kx squared minus alpha x, where both k and alpha are positive constants. Stable equilibrium points, about which the particle oscillates, are located at which of the following? Well, equilibrium points occur when du dx, where the x derivative of u is equal to 0. The x derivative of u is equal to kx minus alpha. And the only time that this equation is satisfied is when kx is equal to alpha, or when x is equal to alpha over k. So this is the only solution, meaning the answer is B. Next, a ball of mass m falls vertically, hits the floor with a speed of vi, and rebounds with a speed of vf. What is the magnitude of the impulse exerted on the ball by the floor? Well, we know that we're dealing with the speeds of these particles. And the impulse is the difference between the two velocities, or between the two momenta. So we have J is equal to delta P. And we initially have a ball moving down towards the floor. So this has a negative velocity. And then at the end, we have the ball moving up, which has a positive velocity. So the change in the momentum is the final momentum, which is mvf, minus the initial momentum, which is m times minus vi, where vi is the speed, and we have an extra minus sign here because it's moving down initially. So this equation becomes m times vf plus vi. So the answer here is C. Next, a particle moves in a circle in such a way that the x and y coordinates of its motion, given in meters as functions of time and seconds, are the following. We wish to find the radius of the circle. Well, a circle is described by x squared plus y squared. Here, using the formulas to the left, x squared plus y squared is 25 cosine squared of 3t plus 25 times the sine squared of 3t. But both of these have a 25, so we have 25 times cosine squared 3t plus sine squared 3t. But there's a trigonometric identity which says that this quantity is always equal to 1. So x squared plus y squared is equal to 25. Since this is the equation for a circle, we know that 25 is equal to the radius squared. So the radius of the circle is the square root of 25, or 5. So the answer here is C. And finally, which of the following is true of the speed of the particle? Well, finding the velocity of the particle, we take the velocity in the x direction, Vx, is equal to dx dt, which here is equal to negative 15 sine of 3t. And Vy is equal to dy dt, which is equal here to 15 times cosine of 3t. Make sure you catch up on taking the derivative of trigonometric functions. Then the speed of the particle is equal to the absolute value of v, which here is equal to the square root of vx squared plus vy squared. Or, writing this out, it is 15 squared sine squared of 3t plus 15 squared times cosine squared of 3t. Since both terms inside the radical have a 15 squared, we can pull that out, so it's the square root of 15 squared times sine squared of 3t plus cosine squared of 3t. But again, this sum of sine squared and cosine squared is equal to 1. So the answer is equal to the square root of 15 squared, which is equal to 15. So the speed of the particle is constant and is 15 meters per second always. So the answer is B. This concludes my answers to the AP Physics C Mechanics 2012 practice exam. Thank you.